Topic sampling cohesive communities and unbounded networks. First of all, I would like to thank Professor Sushmit and Professor PK for guiding me throughout this journey. So let's just jump right into the topic itself. So first, I'll be explaining what sampling really means. More specifically, I'll be talking about snowball sampling because that is the basis of my entire research, which is being presented here. So let's say you have a bunch of nodes that you have information about. By information here, we mean the connections that exist between themselves and the connections they have from outside. So here, the connections between themselves are represented in black, as you can see here. And the connections that they are receiving from outside are shown in blue. So blue nodes. Okay, sure. So yeah, the connections of the seed nodes here are represented in blue. Now, given all this information, our task is to choose one of the nodes from those blue nodes and sort of include it in the network that we know of. So here, as you can see, from this information that we had, I chose this node, which is being shown in red here. And by sampling or choosing that node, essentially, I also get information about its own connections. So here now these two nodes are being added. So in this case, I have sampled this particular red node. Similarly, I can sample more and more nodes. So in the second iteration, I chose this node, and then I get the information about the next node, which is connected to that sample node. So in this case, after two iterations, our resultant network has 5 nodes from the initial 3 nodes, and we have information about all of their neighbors. So in a way, it's called snowball sampling because as with more and more iterations, we are sort of gathering nodes from their neighborhood more and more till like how much ever nodes we want. Now coming on to the problem statement itself, it's about sampling a cohesive community around seed nodes. So given a set of seed nodes, or which we can also call seed network because we have information about their connections. So over here on the right, we see that the blue nodes are again their first hop connections or their immediate neighborhood. So given this information, I want to know what other nodes sort of form the main cluster around these seed nodes. So if we see here, first I will explain one of the other methods which is usually being used, and it's called breadth first search, which is the very basic form of snowball sampling. So using that, how will we do this cohesive community sampling around these given seed nodes? So again, we have the first information, we have a bunch of seeds and we have their connections. From that, first we gather the first layer of nodes, which is like the immediate neighbor of the seed nodes. So here we have all of those shown in red, and we have a few more nodes which have been added. Why? Because these are the connections of those red nodes. So after getting that first layer, now we get the second layer. In this case, getting the second layer was enough to get the entire network. So now that we have the entire network, we run community detection, and from that we get the required clusters. So after this stage, we can take only the cluster that we need for our studies and do whatever we want after that, like the further processing. But this can be very computationally expensive. Why? Because after getting like the required seed nodes, you have to get the entire network first. Then you need to do community detection on that. And then you have to sort of purge all the other nodes and keep only the cluster that you need. So instead of that, we propose another method, which tries to get one cluster at a time from the very beginning itself. So our proposed method is based on the maximum adjacency principle. And now I will illustrate how it exactly works. So we have the same information at the beginning itself. Now, if I ask you which blue node is the most connected to the black nodes, my guess would probably be this one because it has the most connections. So this is a very simple network, undirected, unweighted. And over here, we are checking which node is most connected to our seed network. So over here, we just take this node and we sort again, we try to sample this node. So this node is a part of our network now. And from that, we get information about its networks. So if I ask you which node is most connected to seed network and this first sample node, my guess would probably be this one. So in this way, we are sampling this one cluster first, and then we move on to rest of the network. So over here again, our aim was to sample that one cluster, which is the cohesive group around our seed nodes, which we're able to do by simply following the maximum adjacency principle in an iterative manner, and we get the first cluster. Now, similarly, we get the second one by following the same principle. Because over here, if I ask which node is the most connected to this entire yellow network, and the seed nodes. My guess would probably be something from this cluster itself. Why? Because it is those nodes are the ones which are surrounded by or which are more closely connected to the yellow group and other seed nodes. So yeah, in this way, we are able to sample one cluster at a time. So we have the third cluster, fourth cluster, and so on and so forth. So the good thing is that we are not really gathering any unnecessary nodes. And since our aim was to get that cluster around the seed nodes in the first place, that is what we're directly addressing. Okay, so yeah, this was the method that we proposed. And to test how it works, we tried to look at two settings. The first one in the synthetic, we tried to create synthetic network using stochastic block models, which I will explain now. And then we also, since we also need to test if this method works in real world settings, we implement it on Twitter, on a Twitter real world network. So first, I will explain how the synthetic network looks like and what all different configurations we tried, and if there are any edge cases or like in what conditions does our sampling scheme work and in what it doesn't, and so on and so forth. So first, let's look at what a stochastic block model is. So in this, we give it mainly two pieces of information. So in this model, we try to provide what are the group sizes or like the what are the cluster sizes, that how many nodes belong to which cluster. So for example, in this case, out of 90 nodes, we create three groups. And these three groups have 25 nodes, 25, 30, and 35 nodes each. And after that, we need to define how are they connected. So within the cluster itself, how are the edges connected? How are the nodes connected to each other? And between clusters, what is the probability of an edge being there? Because essentially what a cluster means is that the nodes are more likely to be connected within the cluster than outside the cluster. And this is exactly what we use. So in this particular configuration, the block matrix, the block matrix tells us, if we look at the diagonal elements, it tells us the intra-cluster probability of an edge existing. So over here, 0.8 is essentially that. And then 0.05, the non-diagonal elements that we see, is that between every two clusters, this is the probability of an edge existing. So based on this particular configuration of the model, we get the network as we can see on the right. So you can see that the cluster itself is the denser region of the network, and between the clusters, we don't see as much density. So now I will move on to the configurations that we tried, because essentially we wanted to test the limits of the sampling scheme, in what cases it works and in what cases it doesn't. So yeah, moving on to the configurations that we tried. So first is the group size itself. For group sizes, we wanted to see if there's any effect of group sizes being different versus if all the groups are the same sized. So the first two settings that we see is we have four groups of 400, 800, 1200, 1600 sizes. Second, we increment all of them by 400 because we also wanted to see if the group size itself matters or not, or is it just like the ratio between all the sizes. Then in the third setting, we see when all the groups are same sized and there isn't any particular distinction between them. And now the second task for us was to get the block probability, because this is what really defines how the connections are made in that entire network. So to mimic the real world setting more, we kept the average degree constant, which is 10, and it actually mimics a bunch of social networks. And the second task for us was to figure out the probability between different clusters. So for that, we tried to keep the same ratio. We tried to keep a constant ratio of intra to interblock edges. So what it essentially means is that for every edge that goes within the cluster, how many edges are going outside it? So the first number that we see here, 1 by number of blocks minus 1, it means that if there is a node in some cluster A, so for every edge that goes within the cluster A, we have one edge going to all the other clusters. So 1 to B, 1 to C, 1 to D, and so on and so forth. So this is the setting where we don't really have any cluster division anymore. And if we look at, let's say, the ratio 1, it means that for every edge that goes within the cluster, we have one edge going to one of the clusters outside. Okay, and since in our sampling scheme, we need seed nodes in the first place. So the third configuration that we had to look at was how to select the seed nodes. Yeah, so for the first two setting of group sizes where we have different size communities, we use the following setting where we take 20 or 50 seed nodes per block, and we only take seed nodes from 2 blocks at a time instead of all of those 4. Then the next setting that we had is for this particular setting where we have 8 groups of 1,000 nodes each. Okay. So in that, we want to see how it will work if we have the minimum seed nodes possible, which is 1 seed node per group. And then like we change a few things to see how if there is any change at all. So now I'll go on to results, how we see our sampling scheme works in the following different configuration or even combinations of these configurations. Okay, so over here, I will first show what the ideal case looks like. In an ideal scenario, how will the sampling scheme work? And for that, we use the configuration where we have 8 groups of 1,000 nodes each. And the ratio of edges of intra to intra cluster edges is 4. And in this case, we have 1 seed node per block. So first, let us look at the community evolution. Also, I'll be using the terms group, cluster, community like interchangeably. Okay, so if we look at community evolution, we see if we look at this region from 0 to 1,000 time step. So time step is nothing but the iteration itself. So in this particular case, we see that the community 0 is growing steadily, which means all the nodes that we are sampling in that 1,000 time window, all of those belong to community 0. Then next at 1,000 time step, we see there is some competition, so to say, between different groups. So it's possible that multiple groups are well connected to community 0, and all of them are competing to get sampled first. So we see there is some competition in the initial few time steps, but after that, community 3 sort of emerges as a winner, and we see that 3 is the one that is being sampled. So similarly, these slopes indicate that the node of that particular community is being sampled. And this is exactly what we wanted. But to understand it in a better way, consider a scenario where you do not know which community a node belongs to. So in that case, we don't really have these colors to know what community is being sampled. So we can't really get that plot which you can see on the left. Instead, we now look at what is called a network boundary. So network boundary is nothing but just the number of edges that connect your sample network to its outside. So in this case, if we see, even if we ignore the colors, we see that there are a few inflection points, so to say, that we see a parabola type curve, and then there is a sharp inflection point followed by another parabola type curve, and so on and so forth. So now if we compare the plot on the right with the plot on the left, we see that these inflection points correspond to the points where a new community is being sampled. So even if we do not have any information about what group a particular node belongs to, by just getting that boundary versus time step plot, we will be able to sort of have a cutoff that, okay, I have one cluster now, and then I can sample the second one, and so on and so forth. So yeah, now, but after this ideal case, we should also look at the worst case just to have a better comparison and see what extremes we're looking at. Now, going on to the, okay, so with the same configuration, we now look at random sampling. So you have a seed node, and from all of its neighbors, you randomly pick one at a time. So in each iteration, you're just randomly picking a node from the neighborhood that you know of. So again, if we look at the community sizes, there isn't really any distinction at all. All of them are increasing almost uniformly. And even on the right, in the boundary, there is no particular distinction. We just see a parabola shape, which means that we start sampling, the boundary is increasing very sharply. And then as and when we exhaust the network, the boundary again goes to 0 because there is no outside left at that point. So yeah, looking at these two cases, now we have an understanding of what the worst case scenario looks like and what the best case scenario looks like. Okay, but now we also need to check what is sort of the point between these two where our sampling scheme almost works. So to test that, we use the following configuration of different block sizes with 20 seeds per block. And in this case, we use the value of ratio as 1. So that ratio is the value which is defining how well the network is clustered, or like how distinct are the different groups in this network itself. So ratio of 1 essentially means that for every edge that is within the cluster, we have one edge going outside. So in this case, as you can see on the left, the evolution of community sizes plot, we are able to get the first community well. After that, there is some competition, but even the distinction isn't that clear. Like there is, when we are trying to sample the red community, there is significant contamination from the purple and green ones. Now, if we look at the boundary plot that we were using to sort of mark a cutoff point of where sampling should end, or like where the cluster is being sampled and so on. So on the right, we see that at this around 1000th time step, or like more like 800 time step, we are able to see a distinct point, but after that, not so much. Again, we are able to see some sort of inflection point around 2200, but that's not very clear, so to say, as compared to what we saw in the ideal case. So this is what we will call a limiting case, that we're able to sample the first community, and after that, the sampling scheme doesn't really perform that well. Why? Because the clusters are not very well distinct. Okay. Yeah, so we are able to identify only the first community. Now, that was about the synthetic networks where we have a clean lab setting and we can tweak everything the way we want to. But that doesn't always translate to the real world. So in case of real world networks, we look at Twitter. Our aim was to get a group of politically active users who are active either by tweeting about it or by interacting with tweets that are somehow politically inclined. And we needed such a data set to study properties like spread of influence, for example, because the influence will probably be confined to that cluster, or at least the maximum spread of influence will happen in the group itself than going outside. And the second thing that we wanted to see was structural versus linguistic regularities. So the regularities that we are able to understand from the network structure, like how well people are connected, are they also reflected in the way they tweet? Because tweeting is more of like a linguistic, we look at the linguistic aspects, like what are they tweeting about, what topics they are, and how much engagement they're getting, for example. And in case of structural regularities, we are only looking at how well they're connected to each other and not really how they are connected. Okay, and for this, we use the Dismiss dataset, which contains information about Indian social media influencers on Twitter. Okay, so now for Twitter network, our first task is to build the network itself. Because on Twitter, you can have multiple types of networks. We have follower-following network, who is following whom. And even this can be directed or undirected, that is a different story altogether. Then we have a retweet network, who is retweeting whose tweets and how frequently. Similarly, we can have a likes network and so on and so forth. So the question was, which network do we use? Because all of them do contain some information, but not a single network cannot define all the information that we need. So our answer was try to get them all. So now our task was to build an interaction network based on these four types of interactions that we see on Twitter. We have like, retweet, reply, and quote. So using this photo, I will try to explain what these interactions mean. So over here, if we see this New York Post and this person called Lucas Brown Eyes, they are quoting the post. So they are in a way sharing that post along with their own thoughts. So over here, this entire blue box will be called a quote. And if we look at these three icons below, the first one is reply, second is retweet, third is like. So like essentially just means that, okay, you like the post as it shows there. Okay, and then the retweet icon, it means that the post will be shared on your followers timeline, and it will also have a label that your username retweeted and then the post. So you're not really sharing any thoughts with that post, it's just the same thing being propagated again. Then reply is just replying to that main post. So in this case, this person called Mark Edward is replying to the post by Lucas Brown Eyes. So I hope that is clear. And yeah, now our question was, do we just try to combine all of these four interactions in a way and create one final network? Or we can also weigh them differently. For example, likes is probably less important than a quote because people tend to like many posts, but if we go to, let's say, quote or reply, not as many. In fact, in our data set, we observed that about 76% of all the interactions were likes, and only like 2 or 3% of them were replies or quotes, and retweets were like around 15%. So yeah, now do we just simply combine them by assigning them 4 bits, or is there anything else? So we actually can't. Why? Because by simply combining them, we are assuming that all the interactions are independent of each other. So to explain this particular situation better, let us look at the following example. So this person, let's say they have 3 tweets and we have 2 people interacting with those tweets. So user 1, which is shown in red, and we have user 2 in blue. So let's say user 1 and user 2 both like and retweet tweet 1. For tweet 2, we have interactions only from user 1, which is a like. And for tweet 3, both of them retweet, but only user 2 likes. To see this in a better way, we have a tabular representation on the right, where for all the 3 tweets, the total interactions that we're getting from both the users are the same, but the tweet-wise interactions that we're getting are different. So is it right to say that both of these situations mean exactly the same thing? Because if we just simply combine the different types of interactions, that is what we're signaling. But we don't really have any reason to assume that they mean the same thing, because people are interacting in different ways and there can be different meanings to them. For example, if T2 is some very viral tweet and that's why user 1 interacted with them, it's possible that the blue person does not really sort of relate to that tweet. So it can mean different things and we cannot assume there. So yeah, our answer to that question was not necessarily. They're not necessarily interacting in the same way. So now our problem becomes that how do we really use those 4 types of interactions and get a network which captures information from all 4 of them? So next we try to model interactions. So instead of looking at all 4 interactions in different ways, we try to look at all of them together. And how we do it? By using a 4-length vector. So this one vector represents what all interactions a user has on a tweet, and it captures information about all of those interactions in one go. So using this, we get 15 types of 15 ways that someone can interact with a tweet. And to explain it better, let me show some examples. So over here, 0011, it indicates that a user quoted and replied to a tweet. Then 1110, it's like the person liked, retweet, and quoted that particular tweet. So all of them will always be in the order like, retweet, reply, and quote. So if we have this 4-length vector, we know how exactly a person interacted with the tweet. Now, if we go back, over here, instead of having these 2 separate interactions, we just have one 4-length vector. In this case, it'll be 1100. And over here, it'll be like 1000 and so on. So instead of dealing with them separately, we are able to get all of that information in one go. And instead of having 4 types of interactions, now we have 15 of them. So now we need to look at these 15 interactions in a separate way. And so remember the way I mentioned, we can have a retweet network and a like network and so on and so forth. So at this point, we have 15 such interaction type networks, where one interaction type is one value of this 4-length vector. So we'll have like one network, so to say, for 1000 and so on and so forth. Now we move on to, okay, so it can be understood in a way as we have multiple layers of networks. All of them have the same nodes, but the edges are different because edges are the ones that represent how is someone interacting with someone else. Now our task is to combine all of these layers into one, which will be the final network that we use our sampling scheme on. And how do we do that? By having one weight per layer and try to combine all of them. Okay, yeah. So now I'll go on to how we capture this user behavior through weights, which is basically how do we get these weights in the first place? Because we have 15 different types of interactions and we need to see which one is how important. The main intuition that we have is the more common the interaction type is in our data set, the less it should be weighed. So to have a better example, let's say likes. We almost 75% of the interactions that we saw were likes. So it means that likes are not really that important to show if you agree or disagree with someone. And instead, some other form of interaction like reply or quote, that is a better metric. And now we want to capture this behavior of how frequent an interaction type is at a global scale and a local scale. So what this means is I will go on to that soon. But yeah, so to address this, we need to introduce different types of frequencies or normalizations, where one of them deals with the global one of them deals with the local scale, and so on and so forth. So what this essentially means is that at a global level, we simply look at how common that interaction type or that 4-length vector is in our data set. So on the right, the formula is nothing but the small n of Small n of x represents what is the number of 1000 in our data set, and capital N means how many interactions are there overall. So this way we're able to get a global behavior, or like a global understanding of what is the distribution between different types of interactions. And intuitively, it means if we choose an interaction between a user and a tweet, what is the probability of, of that interaction being x, where x is one of the values of that 4-length vector. Now we also need to see local behavior through the perspective of a source of interactions and a target of interactions. So we do, so on the right, we look at that formula. Over here, this term nix, it means for the source node I, how many times have they interacted in X manner divided by all the tweets they have interacted with. So over here, we're doing nothing but trying to get a value for an average source of interactions. What is the frequency distribution between all the interaction types? So if I am interacting with many tweets, for all those 15 interactions, how many times am I doing, say, only likes or like and retweet in one go, and so on and so forth. Similarly, we can draw a parallel for target normalization. Over there, it's nothing but for an average target of interactions, what is the frequency distribution between all the interaction types? Okay, so now we have these three distributions, so to say, where two of them represent what the interactions mean at a local level, and the first one represents what it means at a global level. Now, how do we really combine them all? Because in the end, we just want one set of weights. So to find that final distribution, we try to sort of predict another distribution, which is at a minimum distance from all the three ones that we saw earlier: global, source, and target. And mathematically, this is same as mean of the three distributions. So now we know how common an interaction is, and the weight can simply be, we can simply calculate the weight by getting reciprocal of these frequencies. Okay, so now that we have the weights, our first task of building the network is done. And now the second was just simply sampling it. And for sampling, we use the same thing, maximum adjacency search. But it is also important to understand how sampling in this network is different from sampling in the synthetic network. The first key difference is direction itself. Because in Twitter, we have directed edges, which are coming from person who is interacting with the tweets to the author of the tweets. So intuitively, this would mean if I'm in the sample network itself, we are looking at people who are being influenced by me, for example, like if because they are interacting with my tweets. Then the second difference we have are the weights itself, because like the weights that we calculated earlier, they are telling how important an interaction is or how strongly someone is interacting with another user. And the third thing we have is we have an unbounded network. In case of the synthetic network, we knew how many blocks are there and how many nodes are there in each block and so on and so forth. But in case of Twitter, that is not the case. And in synthetic network, since we are the ones who are creating the network, we know what is sort of the group distribution, how many groups are there of how many nodes. But in case of Twitter, we don't really have these ground truth communities. So what we do is we just simply have community detection on the sampled network and use those as our community labels. So now after executing the sampling scheme, our results are somewhat like this. And they do look kind of different from the synthetic network, but there are reasons for it, which we'll explain earlier, mainly because it's an unbounded network and it is a directed one. Okay, first, let us look at the plot on the right. We see that after this particular time step, there's a sharp increase, then plateauing, then sharp increase, plateauing again, sharp increase, plateauing again. And corresponding to these 3 points, if we see on the left, the first one, which is around 400 time step, we see there's a sharp increase because the orange community started being sampled. Then at this point, around like 700, we see that the blue community started sampling. And again, around the 2000 time step, we see that it's because this light green community started being sampled. So at those 3 points, we are able to see these sharp increases. But on the right, we see that there is also a lot of noise. For example, if we look at this particular point of 1297, and we see the same point on the left, we see there is a slight spike, but it's similar to other ones which can also be classified as noise. So is it really necessary to make an inference from there, even though we are seeing that there is some community that started being sampled at that point? But we can't really distinguish these kind of points from, let's say, noise. So that's why it's important to look at the points like 344, 713, and 1929 over there, where we are seeing that sharp increase in boundary, and we are able to sort of have a mark that, okay, this is where a community started being sampled. Okay, so and to confirm that this is really happening and that we are getting cohesive network or we are getting like one big community when we start sampling, we also wanted to look at a few other properties. Mainly, we wanted to look at the clustering coefficient because they try to tell how well clustered a network is, both at a local level and a global level. Then over here, L means the average shortest path length, and K means the average degree. So, okay, and another thing is that these three are different types of priority-based sampling schemes itself, but just that the interactions are modeled in slightly different ways. And the four schemes that we see here are random sampling, where D means direct. Okay, so I'll just explain. So we have two different configurations. First is direct or staged. So in direct, we have information about the neighborhood of the sample network, and we try to choose nodes from that neighborhood directly. But in case of staged, first we choose a node from our sample network, and then we look at its neighbors. So it's in a stage with that. First we have that node from the sample network, and then we're looking only at its neighbors and not necessarily others' neighbors. Then we have U and W. U means unweighted, W means weighted. So here by weight, we just add probability distribution, where probability distribution is defined by the weight, by how that particular node interacts with our sample network. Okay, so here we see that priority-based sampling gives a more cohesive network, so to say, than any other random-based scheme. So the basis of making the statement is mainly these values, the clustering coefficients. So we see here that we get the maximum of 0.4, which is way higher than any of the values that we see in random sampling. And similarly, in case of global clustering coefficient also, where we see a factor of almost 20. And then the next observation that we have is that in the prioritized sampling scheme themselves, audience facing or AF variant is giving the best results. Especially, it's getting the highest average degree because the average degree for, let's say, the distinct sampling variant was only 12.97, and we're getting almost double of that. And now there was also a surprising result that we are seeing from this particular table, mainly this value, which is the average shortest path length. So in a cohesive group, this average shortest path length should be the minimum if we sample the cohesive group as required. But in this case, we see that a random sampling scheme is giving better results than a priority based. But it should be noted that even in this case, we are using priorities through this weight factor over there because that weight is essentially giving us the probability distribution based on those weights that are being used in priority. Okay, so yeah, from this table, we are able to see that our sampling scheme, based on a few other checks, we are able to see that our sampling scheme is giving a very cohesive group indeed. And yeah, so that is mainly all. And now moving on to the conclusion, we discussed that how we propose a sampling mechanism to give cohesive group around a given set of seed nodes. Then one interesting thing is that we can also use this particular technique as a seeded community detection because what are we doing? Just taking a seed network and we get a community around them. So if we have a bunch of seed networks and we are able to get like one community at a time, we don't really need to do community detection on top of that to know, okay, where is that particular partition? So yeah. And then we also propose a method of integrating different modes of interactions, like retweet, reply, quote, how all they can be combined to create a separate interaction network. And we also provide Twitter datasets for which we sampled during this study. And now moving on to applications, when I was discussing this particular project with a friend, he suggested that we can even get terrorist networks from such an idea. Because if you have information about, let's say, 5 or 10 terrorists somehow, and you know about connections between them and people they're connected to in some way, you will be able to quote unquote sample more terrorists. You'll be able to identify what group they're part of and how well they're connected. Because otherwise, just getting information about everyone and then trying to filter, okay, who is a bad actor and who is not, and so on, that can be very time consuming. So such applications do give us confidence in this particular sampling mechanism. However, there are also a key limitations, mainly for the real world experiments that we did. Uh, for example, the baseline comparison, when we have the labels that we got for community, those were the labels that we detected after running community detection on the sample network itself. So they aren't really the ground truth labels. So we don't have that ground truth to compare to. So yeah, that is one of the things. And the second, yeah, second is basically that. And okay, so the other thing that we could do is try to compare other sampling schemes which exist for this particular task, but we could not do it because the Twitter API shut down, and so we couldn't really access that data anymore. Okay, yeah, so that was mainly my conclusion. And to address the thesis reviews, the first one was thank you, ma'am, for sharing the reviews. It's from Nime, ma'am. So first, I would address the first paragraph itself, which mainly deals with user attributes, which we discuss in the future work section of the thesis. So over there, we use the given data set and we try to see how we can predict user attributes of other people using that particular data set. So in this particular scenario, user attributes can be anything. For example, age, sex, location, or topics to tweet about, and so on and so forth. So yeah, your comment, if I understood correctly, it deals with like the messiness of context of, because in our particular study, we use how the context of the tweet, and we use that to craft attribute of the user. So to give some context about it again, Twitter itself provides us context annotations for all the tweets. Okay, not really. Okay, so for tweets, Twitter provides us context annotations, which basically tells what topics that tweet is talking about. Now, these context annotations are actually sourced from a specific list which has about 80 categories and thousands of different topics. And from that, they pick what topic shows it the most. So, for example, one topic can be politician, comma Narendra Modi, where politician is the category, Narendra Modi is the specific thing that is being talked about in that particular tweet. So, using that, we were able to get what topics a person is talking about. But the catch is that not every tweet of everyone will have a context annotation. In fact, we saw that only it was mainly in English that we see context annotations and not really in any other language. Or even let's say in English, we are able to see um, some sort of like coverage of context annotations, but not so much. So in this case, we are able to work with that limited information, but we don't really have a way of verifying if that is enough or not. So one thing which we can do is to also account for that information itself, that how many of their tweets actually have a context annotation. And in this case, we use a tweet attribute, which is the context annotation, to create a user attribute. So tweet attribute was the topics, and using those, we create a user attribute. Now we had to do this because for the users themselves, we didn't really have a lot of information. So on Twitter, we can't get information about your age, gender, and so on and so forth because it's very private, of course. So we could get information about, let's say, location, but people can put any location. So in our data set, we saw that people have location like universe, which is not really helping anyone. We're not able to know anything specifically about them. So that information is practically no information. So yeah, things like that. And for that, because of that reason, we had to use tweet attributes to create our user attributes. But we can actually do the opposite also. For example, if we assume that the location is a good enough attribute, that we have good enough values there, we can use information from that user attribute location to the tweet attribute location, and then we can see how they compare. For example, if we can even get an idea of if the user is traveling. So those can be some interesting things that we can do. Um, yeah, so that was mainly my comments about your review, and thanks a lot for that. And the second is I will be addressing Professor Kshitij's reviews. So about the 3 points that we see here, those will be thank you for them, and those I will address them in the final revision of the thesis itself. And the last point about that we can also use data sets other than dismiss, definitely. And that example about trying to identify terrorist networks, for example, I think that can also be a good use case over here. So in our case, we were trying to get people who are politically active, but we can definitely have other networks also. And I think it'll be interesting to see how this sampling scheme compares in like an online social network setting versus an offline one. So that was all from my end, and a big thanks goes to many people here, Professor PK, Sushmita ma'am, then thank you examiners for taking your time to review this thesis, and also Professor Ulrich Brandis from ETH Zurich, who we collaborated with for this particular project. Then my co-authors, Meher, Abhijit, Riyansh, Nidhi, my family, friends, some of them are also here. And thank you all for coming to this talk, and I hope you gained something.